Greetings, everyone. Since it's already 5, let's begin our eighth live session on the semiconductor devices and circuits. The course is being taught by Professor Sanjeev Sangadan, and I am TAing the course. I'm a PhD student at Electrical Engineering Department, IIT Kanpur. So, let us begin by solving our assignment 6, question number 1. So in here, we can clearly see that we have been given some charge profile. And the charge profile, it's mentioned that this is one-sided silicon with p side highly doped. And we have been given 1 by Cj square versus the Vr, where Vr is the reverse bias voltage. So that plot looks like this 1 by Cj square over versus Vr. And the the permittivity of silicon is given to be equal to 11.7, and also the slope of the graph is given to be equal to 6.15 into 10 raised to 15 farad per centimeter raised power minus 2 per volt. So let us solve this problem by simply using the depletion width relation. We know for this PN junction, for the PN junction, depletion width, answer for question number 1. Depletion width for PN junction is simply given by where this WD is the depletion width is equal to 2 times epsilon naught into epsilon R. This is the relative permittivity times built-in potential plus the applied voltage divided by the electronic charge, and this whole multiplied by 1 by Na plus 1 by Nd, acceptor and donor concentrations. Now, for this, since it is given that this p side is highly doped, we will be having an A much greater than Nd. So this will mean Na plus Nd will approximately be equal to Na. So the term 1 plus Na plus 1 plus Nd will simply be Na plus Nd, which will be Na divided by Na and D. This Na and Na will go. It will simply be approximately equal to 1 over Nd. So let us put that in the depletion width expression. So we are left with 2 times epsilon naught epsilon R VBI plus VR divided by Q and D. Now this junction capacitance is simply Cj is simply epsilon naught epsilon R, that is epsilon S divided by the depletion width. This is per unit area, what we are considering over here. It would mean Cj will simply be equal to epsilon naught epsilon R divided by 2 times epsilon naught epsilon R VBI plus VR. This will be under the square root into Q and T. So the expression will simply become epsilon naught epsilon r q and d divided by 2 times VBI plus VR. This will be the expression for Cj. But we are giving the plot for 1 over Cj square. So let us take the reciprocal and square this thing, since this is under the square root. This whole thing is under the square root. If I square this, it will simply become 1 over Cj square 2 times Vbi plus Vr. This will be divided by q times epsilon naught epsilon r and d. Now this 1 by Cj square will be equal to 0 when Vbi is equal to minus Vr. From this, from first equation. So it implies, if we see the graph, this graph intersects the x-axis, that's the voltage axis, at minus 0.725. It means that 1 by Cj square Vbi will be equal to minus of minus 0.725. It will mean Vbi is equal to 0.725 volts. So we have got the value for VBI, that is the built-in potential. Now, since in the problem we are required to find the ND, that is a doping concentration, donor doping concentration. So for that, we will be using the slope of this graph. So if we see, the slope of the graph is simply, if I see from this equation, it is simply this factor. Slope is simply 2 by 2 times epsilon naught epsilon r and d. This is the slope for the graph. And or we can write nd is equal to 2 over q epsilon naught epsilon r times the slope. So we know the slope value is 6.15 into 10 raised power 15. So we can write this nd to be equal to 2 by q is 1.6 into 10 raised power minus 19 epsilon naught into epsilon r 11.7 for the silicon as it's given 8.85 into 10 raised power minus 14 farad per centimeter square into the slope. Slope is 6.15 into 10 raised power 15. 6.15 into 10 raised power 15. So let me solve this expression to obtain the value for the ND, donor concentration. So it comes out to be equal to 1.96 into 10 raised power 15 per centimeter cube. So this is the donor concentration that we got in the problem 1. Now I have not put the options over here as this was some lengthy question. Now let me move towards another problem which states that in question 1, what is the concentration for the acceptor atoms. So there is a simple way to go about this. Since we know the VBI, we can use simply the relation which is VBI is given by KT by Q, which is the thermal voltage, ln of Na, where Na is the acceptor and Nd is the dopant concentration, and this Ni is simply for Ni for silicon. Now, if I take the values for this, I will simply write it in terms of the exponential, taking exponential on both sides. It would mean that I will be having an I square exponential of VBI by KT into Q. This will be NA and D. This would mean Na is simply equal to Ni square exponential of VBI Q by KT into divided by the Nd. Now let me put the values for this concentration. 10 to the power 10 exponential of VBI, we got 0.725, so it is 0.725 divided by the thermal voltage, it is 0.026, for temperature equal to 300 Kelvin, divided by ND we got was 1.96 into 10 raised power 15, 1.96 into 10 raised power 15. So this Ni will approximately be equal to, let's solve this expression. So it comes out to be equal to 1.64 into 10 raised power 17 centimeter cube. So it is the option A, that is matching. So we will select option A, 1.64 into 10 raised power 17. Yes, 10 raised power 17. Now let's move towards another problem which states that there is some diode which is in forward bias, and the DC current flowing through this diode is 13 microampere, and we have the voltage, the thermal voltage, that is 26 millivolts, and the junction capacitance of this PN diode is at given to be at some operating frequency, that is 1 nanofarad, and that frequency is given to be equal to 10 to the power 6. So radians per second, be careful about that. So we are required to find the magnitude of the small signal current through this diode. Now we know the dynamical resistance, the AC resistance, let me write it down like this. AC resistance is for this diode is simply given by Vt by Id, where this Id is the DC current. So Vt is 26 into 10 raised power minus 3, and this Id is 13 into 10 raised power minus 6. So it will imply this Rd dynamic resistance is simply equal to 2 kilo ohms. So let's insert some slides. It would mean that this circuit, let us draw the equivalent circuit for this diode. Now it will simply mean we will be having some AC source, and the AC source has strength of 5 sine omega t, 5 sine omega t, whether it's in millivolt or not. Yes, it's in millivolts, and this will be the resistance, the dynamical resistance Rd equal to 2 kilo ohms, and this will be some capacitance minus J Xc with some reactance. reactance, and there is other resistance with value of 100 ohm. Now, if this is the AC current that is flowing through the circuitry, so this magnitude of this AC current will simply be given by the VAC over the impedance. Let us say this whole impedance is equal to Z1 and this is equal to Z2. So this will simply be Z1 plus Z2. Now this Z1 is simply the parallel combination of this capacitance, reactance and this RD. It would, and this Z2 is having the value of 100 ohms. It would mean this XC will simply be equal to 1 by omega C, where this 1 omega was given to be equal to 10 to the power 6 and this C is given to be equal to 1 nanofarad. So this is 10 raised power minus 9, or the XC is 10 raised power plus 3 simply. So if I solve for this Z1, Z1 will simply be equal to minus J into 10 raised power 3 with 2K resistor divided by 2 into 10 raised power 3 minus J into 10 raised power 3. Or simply I can write it like this, minus J into 2 divided by into 10 raised power 3 to minus J. This is the impedance of Z1. Now this impedance is in series with the Z2, which is just a resistor, 100 ohm resistor. I can simply add those resistances. Z1 plus Z2 will give me minus 2 into 2 into 10 raised power 3 divided by 2 minus J plus zero point 0.1 into 10 raised power 3. Since that is 100 ohm, I can write it in terms of kilo ohms. It would simply imply that minus 2J plus zero point 0.2 minus zero point 0.2J into 10 raised power 3. This will be outside divided by 2 minus J. Let me add some slides. So this will become zero point 0.2 minus 2 point. This is minus, this is 0.1. Sorry, this is zero point 0.1. So it will become 0.2 minus 2.1 J will become zero point 0.2 minus 2.1 J. This will be multiplied by 10 to the power 3 divided by 2 minus J. 2 minus J. So this is the impedance of the circuit, total impedance. Now the magnitude of this impedance will simply be given by the 10 to the power 3 root of zero point 0.2 square plus 2.1 whole square divided by 2 square plus 1 square under root. Now let me find the magnitude for this. It should simply be equal to 0.943 into 10 raised power 3. Now IAC will simply be equal to VAC by Z1 plus Z2. It would mean VAC is having the magnitude of 5 millivolts. So it is 5 into 10 raised power minus 3 divided by 0.943 to 10 raised power 3, or the IAC is simply equal to 5.3 microamperes. Let's check the options. So it's option A, which is matching. So we will go with option A. Let's move towards another problem, which states that we have we have some charge profile that is given, and this charge profile has the donor concentrations of the order of 10 to the power 16 and of the order of 10 to the power 15. Now we have been told to find the built-in voltage from these corresponding um, uh, uh, charge density profiles. Now let us simply solve this problem by using the band diagram concept. Since the left hand side is having high concentration, the Fermi level will be closer to the conduction band in that case, and since the right hand side is having the concentration of 10 to the power 15, the Fermi level will be bit farther as compared to the left hand side. So the if I draw the Fermi level, let me draw the Fermi level first so that we understand it properly. And on this side, we will be having the Fermi level closer, and on this side, it will be not that much farther, it will be bit far. Similar is the case since the material is the same, the band gap will remain same, and thus this will have the band bending that will be occurring over here. So we will be having structure band structure like this. If now I draw the intrinsic Fermi level as well, that will look like, sorry, intrinsic Fermi level EFI. This is EV2. This is EC2. So from this band diagram, if I draw the depletion weights, if this is taken to be the origin x equal to 0, then this much amount of band bending has occurred, where this is will be the built-in potential. This will simply mean that I have to solve the for the charge densities to get this built-in potential. I can use the potential balance simply to get this built-in potential. Let me simply say that since this QBI, Q5BI, Q5BI, it will simply be the difference of EC2 minus EC1, but EC2 minus EC1 at bulk. This is important, at bulk. So at equilibrium, at equilibrium, this majority concentrations will be given by simply ND1 will be equal to NC, effective density of states at the conduction band edge, EF minus EC1 by KT. And similarly for the right hand side, ND2 will simply be given by NC exponential of EF minus EC2 by KT. So if I now solve these two by simply dividing the first and the second, ND1 by ND2, it would simply mean that I will be having exponential of EC2 minus EC1 by KT. Now let us take 1 on both sides. So it would mean that I will be having KT ln of ND1 by ND2 is equal to EC2 minus EC1. there where this EC2 minus EC1 is Q5BI. So KT1 of, I think it was 10 to the power 16 and it was 10 to the power 15. It is 10 to the power 16 by 10 to the power 15 will give me 5BI. This 5BI will simply be equal to 0.026 multiplied by ln of 10. Let me solve this on my calculator and check the results. It would simply come out to be equal to 60 millivolts. This is the built-in voltage. So this built-in voltage is option A. Now let's move towards another problem, which is having some intrinsic region in the middle. Let us zoom this first a bit. It states that the charge profile, we have been given some charge profile where the PN junction is having some intrinsic region in between, such that the width of this PN junction is between minus W to minus 0.5 for N type, and for P type it is 0.5 to W, and between that 1 micrometer we are having some intrinsic region, and it is shown over here. We have been given the doping concentrations Na and Nd to be equal to 10 to the power 15 and Kt by Q is 20 millivolt, and the intrinsic carrier concentration Ni is 10 to the power 10 per centimeter cube. Now we are required to find the built-in voltage. Now let's go about this by uh, drawing the energy band diagram first. It would simply mean, since on the left hand side we are having the N type and on the right hand side we are having the P type, it would mean the Fermi level will be close. Let us draw the Fermi level first to understand it properly. If this is the Fermi level, it should be close to the conduction band on the N side, ECN, and it should be close to the valence band on the P side. So it would mean we will be having band diagram that will be looking like this, and this will be the intrinsic region. Now this intrinsic region is having some this width which is given by minus zero point 0.5 to zero point 0.5, which is 1 micrometer. Let us say this is the intrinsic region. This is the intrinsic region, and this will be the depletion width minus W and plus W on the N and the P side respectively. And this is EV on N side, EV on P side, EC on P side. Now, if I solve for the built-in potential, it would simply mean that this is my built-in potential. Simple. So this built-in potential, this built-in voltage is simply given by Q times phi B is ECP, that is the conduction band edge on the right hand side, on the P side minus EC on the N side. Uh, Let us write down the equations for the carrier concentrations. So it will simply be equal to ND will simply be equal to NC exponential of EF minus EC on the N side by KT for N side, for N. Now for P, it will simply be equal to n I square over n A. It will simply be n C exponential of EF minus ECP by KT. This will be P for P. Now, if I divide these two, let me write it down as A, and let me write down this B, A by B. It would mean that I will be having N A N D by N I square. NC and NC will go, and it will simply be ECP minus ECN. It will simply be exponential of ECP minus ECN divided by the KT, taking ln on both sides. So it would become KT ln of NA ND by NS square is given by ECP minus ECN is equal to Q5BI. Simple. Let me put the values for these. KT by Q, KT by Q ln of NAND by NI square will simply be equal to this 5BI. Let me check the values. It is 10 to the power 15 and 10 to the power 10. It is simply equal to 26 into 10 raised power minus 3 ln of 10 to the power 15 into 10 to the power 15 divided by 10 to the power 10 whole square. This is the built-in voltage. So this built-in voltage, let's solve this numerically. It should ln of t this, this, it should come out to be equal to 0.6 volts. Let us check our options. Which option is this? It is option C. So we will take the option C. Now in question 5, we have been told to find the what is the value of this 2 times W. What is the value of this 2 times W? That is the depletion width that was occurring on the P and N side. Now let me draw the electric field, how it would look like as a function of the position. If this is in the X, this is the field, then the field will look like this, where this is the intrinsic region. This was minus 0.5 and this was plus 0.5. This is W, this is minus W, and this is the maximum value of the electric field. Electric field. These are in micrometers. So this what this area under this electric field will be the built-in voltage. So now let me write it down like this. Built-in voltage is equal to area under electric field. Okay, let's add some slides. So if we calculate the area, this is some rectangle. This is some rectangle with width of 1 and the height of E max, and this is some triangle with base equal to W minus 0.5 and the height equal to Emax. So the area will simply be equal to this phi b will simply be equal to 2 times, if I take the positive side only, Emax into zero point 0.5. This thing I am taking and that is symmetric with this thing. My drawing might not be perfect, and this thing I will be taking. So this will be simply 1/2 of base, that is uh, E max is the altitude and this is the base, W minus zero point 0.5. Someone is here, let me admit him. So this is our built-in voltage. Now let me use this a bit. It will become E max plus, this will simply be uh, zero point 0.5. If I add this with this zero point 0.5, it would mean this will be zero point 0.5 minus plus W. Yes, since this is minus 0.25, yes, it will become 2 times. Now I have got this expression, some expression, and I need to find the value for W, this depletion width. Mm, I have two unknowns in here. This E max is unknown and this W both are unknown. So let us go about writing the Poisson equation for this. Poisson equation will simply be the field will be given by Q times NA W minus X by epsilon naught into epsilon R. I am simply using the Poisson equation over here, and for this zero point 0.5 micrometer, the electric field will be maximum. I can simply write E max occur will occur at x equal to zero point 0.5 micrometer. So I will simply substitute the values for the x and I will get Q times Na W minus zero point 0.5 divided by epsilon naught epsilon R. Now if I use these two expressions, this one and the second, I should substitute E max in first. I will get the expression for the phi b to be equal to Q times Na W minus zero point 0.5 W plus zero point 0.5, which will simply be equal to W square minus zero point 0.5 square divided by epsilon naught epsilon R. So this we already have calculated the built-in voltage. This was zero point 0.6, so this is zero point 0.6 into epsilon naught will simply be equal to 11.7 into 8.85 into 10 raised power minus 14. Be careful about the units. I am doing it into farad per centimeter square. This Na, uh, let us write for the electronic charge first. This Na was equal to 10 to the power 15, I guess. Yes, it is equal to 10 to the power 15. So this is W square minus zero point 0.5 square. Be careful about the units because in here this is in micrometer square and over here I am doing it in centimeters. So we have to be careful while substituting the values. I will just solve it on my calculator. So it would come out to be equal to 38.83 into 10 raised power minus 10, but this is in centimeter square. So this is W square minus 0.15 minus zero point 0.5 square. This is zero point 0.5 into 10 raised power minus 6 meter square meter square. This is squared. It will become W square minus 0.25 into 10 raised power minus 12 meter square, or this will become W square minus 25 into 10 raised power minus 14 meter square. Let us convert the left hand side into centimeter square as well. It will simply be equal to 38.83 into 10 raised power minus 14 meter square. So both quantities are in meter square. Now we can simply add them. It will simply be 38.83 plus 25 into 10 raised power minus 14 meter square. So it would simply be the square root of these two quantities. This 25 is 25 plus 38.83 is simply equal to 63.83. It is square root of 63.83 into 10 raised power minus 7. This will be under the square root. This is meters. This is the depletion width, W. So if I take the square root of this quantity, it would come out to be equal to 0.798 micrometer. This is the value of W. That's what I think we were supposed to do. So what is the value of 2W? So I have to multiply this by 2. 2W will simply be equal to 2 into 0.798 micrometers, and it should come out to be equal to 2 this. It should come out to be equal to 1.596 micrometer. So let us check the option. It is the option D. Now let us move towards the seventh problem. It states that what is the value of the electric field at x equal to 0, that is E max, since this is in the intrinsic region. So let us write down the solution simply, since it is related to the previous question in which we found the electric field maximum. It is equal to the built-in voltage, E max into, it was zero point 0.5 plus W. So this built-in voltage is zero point 0.6. This is E max. This is zero point 0.5 in micrometers, and this W came out to be equal to 0.798 plus 0.798. This will be in micrometers. So this will simply be 0.6 divided by, this will be 1.298 into, this is a micrometer, this will come over here, this will be the maximum electric field. So let us divide the 2, let me divide the 2, 0.6 divided by 1.298, so it will come out to be equal to 0.46 or 4.62 into 10 raised power 5 volt per meter. Be careful about the units, since this wasn't in micrometer. I have kept the units in meter in this problem. So there is uh, no option. No. I think yes, option C is matching. Option C is matching. So we will go with option C. I thought that there is no option, but option C is matching absolutely. So the option C will be the correct to go with. Now let's move towards the another problem. It states that we have been given some PN junction which is doped uniformly with the accepted concentration of 10 to the power 18 and the dopant concentration of donor concentration of 10 to the power 15 per centimeter cube, and we have been given the PN junction area which is 6 into 10 raised power 4 centimeter square, and we have been given that inductances, some inductances placed in parallel with this PN junction. Since we know that this PN junction has some capacitance associated with it, so we will be having an LC circuit. So we have been told to find the resonant frequency of the circuit for some reverse bias voltage which is 1 volt, and we have been given some quantities over here. Now let us solve simply for the resonant frequency हिंदी में ठीक actually there is a problem in that I can मैं हिंदी में भी बोल सकता हूँ और इंग्लिश में भी एक साथ. तो इश्यू यही है कि फॉर एग्जांपल कोई बोलेगा कि आप इंग्लिश में क्यों बोल रहे हो, ये ना हिंदी में क्यों बोल रहे हो. तो इंग्लिश एक कॉमन लैंग्वेज बना दिया, तो मैं हिंदी में भी बोलूंगा और इंग्लिश में भी बोलूंगा साइड बाय साइड. तो इस सवाल में हमें बोला गया है कि एक पीएन जंक्शन है हमारे पास, उसमें डोपिंग की गई है ऐसे कि एक साइड में 10 टू द पावर 18 है और दूसरे साइड में 10 टू द पावर 15 कंसेंट्रेशन रखी गई है, और हमें हमारे पास उसका एरिया भी दिया गया है जो पीएन जंक्शन है. तो हमें पता है अगर हमारे पास एक एलसी पीएन जंक्शन है तो उसके साथ उसका कुछ कैपेसिटेंस रहेगा. तो उस कैपेसिटेंस के बदौलत हमें देखना यह है कि अगर हम एक इंडक्टर उसके पैरेलल में रखेंगे, क्या ये टैंक सर्किट एक्ट करेगा. हाँ, ये टैंक सर्किट एक्ट करेगा. तो हमारे पास एक रेजोनेट फ्रीक्वेंसी आएगी. तो जो वो रेजोनेट फ्रीक्वेंसी रहेगी उस वो हम लिखते हैं इक्वेशन से, वो सिंपली होता है दिस दैट this resonant frequency will simply be equal to 1 by 2 pi root of LC. So 1 by 2 pi root over LC, where this L is the inductance and the C is the capacitance. So simply अब हमें ये करना है कि हमें कैपेसिटेंस ढूंढनी है इस सर्किट की. तो सिंपल है, अब हमारे पास ये है कि हम पहले डिप्लीशन विड्थ ढूंढे, क्योंकि डिप्लीशन विड्थ से ही हमारी कैपेसिटेंस एसोसिएटेड रहती है. सो वी विल बी फाइंडिंग द डिप्लीशन विड्थ फर्स्ट. So this depletion width will simply be given by 2 times epsilon naught epsilon r. This VBI जो कि built in voltage है हमारे पास, VR जो reverse bias voltage है, divided by Q times 1 by NA plus 1 by ND, और ये सारा स्क्वायर रूट के अंदर रहेगा. This whole thing will be under the square root. Now let me put the values for these expressions one by one. Wait a second. So this will be 2 into epsilon naught. I think this was not given in the question. Yes, we have to take it by ourselves. Epsilon naught. Let me first calculate VBI, because I will be needing the VBI to calculate this. So let us calculate the VBI first, then we will go for this WD, the depletion width. This VBI will simply be given by KT by Q ln of NA and D by NI square. तो जो अब हमें हमारे पास जो ये built in वोल्टेज है, इसका वैल्यू हमें पता रहेगा KT by Q का, जो कि 26 मिली वोल्ट है. तो we will simply write this ln of NA and D. तो NA and D हमारे पास रहेगा 10 to the power 18 और 10 to the power 15. तो 10 to the power 18 into 10 to the power 15 divided by NI square. NI हमारे पास है 1.5 into 10 raised power 10. 1.5 into 10 raised power 10. This will be squared and ये हमारा ln में रहेगा. तो अगर हम, so let us solve this for this VBI. This VBI will simply be equal to 26. No, still should be equal to 0.76 volt. तो अब हम जाते हैं अपने डब्ल्यू डी के पास, जो हमारा डिप्लीशन रेट है वो था 2 टाइम्स एप्सिलॉन नॉट हमारे पास है 11.7 जो कि क्वेश्चन में दिया है। तो 11.7 इंटू 8.85 इंटू 10⁻⁻14 फैराड पर सेंटीमीटर स्क्वायर, और हमारे पास वी बी आई जो आया था वो 0.76 है, and we had been given the reverse bias voltage 1 volt, और रिवर्स बायस वोल्टेज हमारे पास है 1 वोल्ट का। तो नीचे हमारे पास we are given the electronic charge 1.6 into 10⁻⁻19, and this whole thing is 1 by Na and Nd. I could approximately write it to be equal to 1 by Nd. Yes, because this concentration is high, so I will simply write it 1 by 10 to the power 15. This whole thing will be under the square root. This from this I will calculate the capacitance. This capacitance will simply be equal to the epsilon naught epsilon r divided by this WD. This epsilon naught is 11.7 into this epsilon, and we have been given the area as well, which is 6 into 10⁻⁴। तो हम टोटल कैपेसिटेंस यहाँ पे देखेंगे तो ये है 6, तो ये एरिया से मल्टीप्लाइड है, तो ये रहेगा एप्सिलॉन 8.85 इंटू 10⁻⁻14। तो एरिया अभी हमने चेक किया था, ये था 6 इंटू 10⁻⁴, 6 इंटू 10⁻⁴ डिवाइडेड बाय WD। तो ये हमारा था WD जो इससे पहले हमारे पास आया था। तो अब हमारे पास हर एक चीज का वैल्यू रहेगा, बस हमें अब चेक करना है कि 1/2 पाई रूट ऑफ LC का वैल्यू क्या है। तो दिस सिंपली शुड be 1/2 pi. This is millihenry. This is in millihenry. This is 2.2. This is 2.2 into 10⁻⁻3. So अगर हम कैपेसिटेंस का वैल्यू अब यहाँ पे पुट करेंगे तो हमारे पास इसका आंसर आ जाए। तो because this is a lengthy calculation, I will be skipping this as we have to complete other two questions as well. So in problem number 9, it states that we have been given an ideal PN junction diode, and this diode is having an current of 2 milliamperes at some temperature which is 300 Kelvin. This is at some condition when the forward bias is of 0.1 volt, and we have been told to find the reverse saturation current. So अगर हम देखेंगे इस सवाल में हमसे पूछा गया है कि अगर हमारे पास एक डायोड है पीएन जंक्शन का, तो उसमें अगर हमने 0.1 वोल्ट का पोटेंशियल दे दिया है तो उसके अक्रॉस, तो उसके बीच में 2 मिली एम्पियर की करंट चल रही है, और ये कंडीशन दिया गया है 300 केल्विन पे। तो हमें बोला गया है कि आप रिवर्स सैचुरेशन करंट कैलकुलेट कीजिए। तो अगर हम रिवर्स सैचुरेशन करंट कैलकुलेट करने जाएंगे, हमारे पास डायोड की जो इक्वेशन रहेगी, the diode equation will look like the ID is equal to I naught, where this I naught is the reverse saturation current, exponential of Q by VA by KT minus 1. So हमें पता है कि ID हमारे पास है 2 मिली एम्पियर, और जो V applied है वो 0.1 का है, और दिस KT by Q जो that is given by 26 मिली वोल्ट। सो हम डायरेक्टली सब्स्टिट्यूट करेंगे वैल्यूज।
So if we directly substitute now these values, this will be 2 into 10 raised power minus 3. This will be I naught. This will simply be exponential of uh, zero point 0.1 by 0.026 minus 1. So if I solve this on my calculator, it will be I naught exponential of 0.1 divided by 0.026. This is 3.84. This is 3.84. 6 minus 1, or simply this is 2 into 10 raised power minus 3 divided by e to the power this thing minus of, this will be 45.99, और simply I naught हमारे पास आएगा 2 divided by 45.99, which is 0.043. It will be 43.5 into 10 raised power minus 6 एम्पियर. ये हमारे पास आएगा रिवर्स सैचुरेशन करंट का वैल्यू.
Any question?
तो जो ये आई नॉट है ये हमारे पास है 43.5 माइक्रो एम्पियर. सो दिस आई नॉट केम आउट टू बी 43.5 micro ampere approximately. So we will go with option A, 43.7. Now let's check the last problem of this assignment. It states that an ideal PN junction diode is a forward bias moderately such that the applied bias is much greater than the thermal voltage. How much voltage is needed to increase the diode current by a factor of 10 at 300 Kelvin? तो इस क्वेश्चन में हमसे पूछा गया है कि अगर हमारे पास एक डायोड है तो उसको हम फॉरवर्ड मोड में बायस कर रहे हैं, तो जो एक और कंडीशन हमें इसमें दिया गया है वो ये है कि जो हमारा फॉरवर्ड बायस का वोल्टेज है वो बहुत ज्यादा है एज कंपेयर टू द थर्मल वोल्टेज. सो इसमें बोला गया है कि हमें कितने वो वोल्ट्स का चेंज करना पड़ेगा ताकि हमारा करंट 10 गुना हो जाएगा एट 300 केल्विन टेम्परेचर. सो जो पहला कंडीशन हमारे पास ये है कि अप्लाइड वोल्टेज जो है वो हमारे पास बहुत ज्यादा है किससे, दे थर्मल वोल्टेज से. सो we will be simply writing this expression that we wrote in the previous question. It will simply by VA by VTH. तो जो -1 का टर्म था, फैक्टर था, वो निगलेक्ट कर लेंगे. That will, the -1 factor will be neglected. So this we have to apply some delta VA. If this delta VA is the additional voltage, this is the additional voltage for increasing the diode current. Okay, 60 millivolt. I have to check. You might be correct. If delta V is the additional voltage, तो हम सिंपली लिखेंगे उस जो दूसरी करंट रहेगी हमारे पास, जो I2 है वो इसके 10 टाइम्स रहेगी. तो 10 टाइम्स I हमारे पास रहेगा I नॉट एक्सपोनेंशियल ऑफ VA प्लस डेल्टा VA डिवाइडेड बाय VTH. तो हमारे पास अब दो इक्वेशंस हैं, तो हम I को रिप्लेस कर सकते हैं by this equation. So we can replace the I by this equation. It will give me 10 times, so it will give me 10 times, wait a second, 10 times exponential of VA by VTH times I naught will be equal to I naught exponential of VA by VTH into exponential of delta VA by VTH. So this will go, this will go, this will go, this will go. I will be left with ln of 10 delta VA by VTH. तो हमने यहाँ पे कुछ नहीं किया है, बस जो टर्म्स हमारे पास थी वो कैंसिल हो गई एंड वी आर लेफ्ट विद, हमारे पास अब रहा 10 एक साइड से रहा और एक्सपोनेंशियल ऑफ डेल्टा VA by VTH दूसरे साइड से रहा. तो हमने जस्ट टुक द लॉग एक्सपोनेंशियल ln e on both sides. So अब ln 10 का वैल्यू हमारे पास जो रहेगा उसको हमें मल्टीप्लाई करना है, ln ऑफ 10 को हमें मल्टीप्लाई करना है VTH से। VTH का वैल्यू हमारे पास रहता है 26 मिलीवोल्ट का, तो ये अप्रोक्सीमेटली बराबर आएगा 60 millivolts. As said by someone correctly in the chat, it will come out to be equal to 60 millivolt. So this is the right option to go with 60 millivolts. So I think we should conclude this lecture for today, as we have already covered the assignment 6. If you have any question, you can ask it in the chat window. And if you don't
Uh,
have any question,
uh,
you can.
Hello, sir.
Mhm.
In the question of resonant frequency,
Okay.
what was the purpose actually? Uh, in a PN junction.
Basically, it is just to get a feel that we are having some capacitance associated with the PN junction. That's what I understood by that thing. Because if there is something which has having some capacitance associated, you can use it as a tuner. And PN junction in reverse bias is used sometimes as a tuning circuit. That's why there is the purpose of that question. It has some practical applications.
Yes, yes, sir. So by controlling the depletion width, we can control that resonant frequency. Hence,
Yes, 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 absolutely.
we
You're
can
absolutely
achieve that
correct.
tuning purpose. Yes, yes,
Yes,
sir.
yes, yes.
Thank you, sir.
If we have no questions, you can leave the so that I can end the session.
Okay, sir.
Thank you.
सर यही सब क्वेश्चन आएगा क्या सर?
आई एम नॉट गोइंग टू सेट एनी पेपर. मैं कोई पेपर नहीं बना रहा हूँ. मैं जस्ट पढ़ा रहा हूँ यहाँ पे. जो असाइनमेंट्स आपके रहते हैं उनमें जो कंफ्यूजन आपका रहता है वो मैं बोलता हूँ आपको. इसके अलावा अगर आपको कभी भी कंफ्यूजन रहेगा आप मेरे को ईमेल कर सकते हैं, तो मैं ट्राई करूंगा अपनी ओर से उस क्वेरी का, उस क्वेश्चन का जवाब देने का. ठीक है.
ठीक है सर.
तो लेकिन मैं क्वेश्चंस फ्रेम नहीं कर. इट्स डन बाय प्रोफेसर.
कुछ सर इम्पोर्टेंट सब क्वेश्चन मतलब है तो.
दिस इज एनपीटीएल सेशन. आई डोंट नो एनीथिंग अबाउट इट. मुझे तो पता नहीं है ना रहेगा उसके लिए. तो let us end this session. I will be removing everyone from the session so that I can end this. Thank you very much for joining this session.